This screencast, I'll be showing the electric field due to a distributed ring of charge. I've made a sketch here, and we can see the distributed ring of positive charges, and we're looking for the electric field at point P. The tricky part about doing this particular derivation isn't really the math or the setup, it's simply understanding in 3 dimensions what's happening here. So we have an XY plane, and we're also projecting the ring out in the z-axis. We can see that there would be a bunch of electric fields going not only down and to the right, but also towards you, the viewer, towards the screen and into the screen. All of those components of the electric field in the y direction and the x direction, as described by x, y, and z here. X and y direction components will cancel out, and I'm only going to be really looking at the leftover component in the z direction. Like many of the other problems, we'll be looking at a tiny little piece or a differential of charge around the ring, dq, and we're going to start with some kind of initial conditions where the linear charge density is the charge over the length of the distribution. In this case, the length of the distribution is equal to 2 pi capital R, where capital R is going to be equal to the radius of the ring. Additionally, and this is probably a hard one to visualize in 2 dimensions, not probably, but it just is. If you take a look at this green line that I've drawn from the origin to our particular location, dq in this case, we're going to describe an additional angle. There are going to be 2 different angles we're paying attention to. One of them we'll call phi, which is from the x-axis to that particular line, that green line that I've drawn. Additionally, there's going to be another angle which we'll call theta, which creates this triangle. It is a right triangle, even though it doesn't look, when you look at the green line, the pink line, and the black z-axis, it doesn't look like a right triangle, but it is. The only reason that it doesn't look like a right triangle is because of the way that I've drawn that green line in 2 dimensions. But it is a right triangle. If we were to look directly down the x-axis, this would be a right triangle. So we know then that the cosine of the angle theta is going to be the ratio of the adjacent side over the hypotenuse. We did this similarly in a previous problem, where we can call this distance r from the differential of charge to point P. We can call this distance z here. And of course, the length of the green line is the radius r. And so therefore, when I go back to cosine of the angle theta, the adjacent side is going to be z, and the hypotenuse is going to be r. But I need to be able to say that I have a right triangle. So let's go ahead, and the last thing that I'll do is write the Pythagorean theorem. C squared is equal to a squared plus b squared. So therefore, r squared is equal to capital R squared plus z squared. So therefore, r is equal to capital R squared plus z squared to the 1/2. And that's going to get substituted in the denominator over here. So I get z over capital R squared plus z squared to the 1/2. Okay, so these are my kind of important initial conditions that I've drawn in pink and in blue and in red. And then the rest of this is just substitutions and a little bit of calculus, but not too much. So now I can say that the differential of the electric field in the z direction is going to be equal to our constant, 1 over 4 pi epsilon naught, or k, times dq, the differential of charge, divided by the separating distance, r squared, and then I'm going to multiply it by the cosine of the angle theta. Now there's a few substitutions I'm going to make. I kind of forgot one up here. I can also say that lambda is equal to dq over ds, where s is the tiny little bit of length of the arc of the ring. And so I can say that ds is equal to capital R d phi by how I've drawn that. So now that I've seen these additional equivalencies related to linear charge density, I can say that dq is equal to lambda r d phi. dq, the differential of charge, is equal to lambda r d phi, r times d phi times lambda. Lambda r d phi. That gets substituted in right there. And this expression for cosine of theta gets substituted right there. And our expression for r squared gets substituted right there. So these three substitutions I can do in one kind of elegant step if you want. The differential of the electric field in the z direction is equal to our constant 1 over 4 pi epsilon naught times dq, which I can now write as lambda r d phi, divided by r squared, where r squared is equal to capital R squared plus z squared to the 1/2, multiplied by cosine theta, which I can write as z over r squared plus z squared to the 1/2. So now wait a second. When I substituted for r squared, this shouldn't have been to the 1/2 here. So we can see that r squared is actually just r squared plus z squared. So I'm going to leave that as it originally was. So now my next step then is to integrate both sides. I'm going to integrate all the little dq's, and I'm going to integrate it from 0 to 2 pi. I'm going to basically go all the way around the circle. And I'm going to pull out some constants. And so when I integrate on the left-hand side, that just becomes the electric field in the z direction. I have some constants. Let's go ahead and identify them. R is a constant. R is a constant. Z is a constant. Lambda is a constant. The only thing that's not a constant, this is a constant, the only thing that's not a constant is dq. Everything else is a constant. So let's go ahead and combine those pieces. By the way, r squared plus z squared times r squared plus z squared to the 1/2 is just r squared plus z squared to the 3/2. So that becomes 1 over 4 pi epsilon naught times r squared plus z squared to the 3/2. And then in the numerator, I'm going to pull out lambda. So I'm going to replace my 1 with a lambda times r times z. And I'm left now with just d phi. So I'm basically going around the circle and I'm adding all these pieces together. I have to integrate d phi between 0 and 2 pi. And so the integral of d phi is just phi, and I'm going to substitute that, both with 2 pi and 0, right? I have to evaluate it between my limits of integration. So if I'm just paying attention to this piece right here, I'll write that off in green. This becomes phi evaluated between 0 and 2 pi, which I can really write as 2 pi minus 0, which is just equal to 2 pi. So now I've integrated d phi, and I'm just left with this constant 2 pi. And so now I can write this as the z component of the electric field is lambda r times z times 2 pi divided by, in the denominator, 4 pi epsilon naught r squared plus z squared to the 3/2. The 2 pi in the numerator is going to cancel out with the pi and reduce that to a 2. And I could finish this and just write as lambda r z over 2 epsilon naught times r squared plus z squared to the 3/2. Now, if I wanted to, I could substitute in lambda is equal to, again, if I didn't want my answer in terms of linear charge density, I could say that lambda is equal to q over 2 pi r. We kind of established that in red initially up here. So if I substitute that in for lambda, if I wanted to, it would be acceptable to leave it in this way. But if I was specifically asked to give it in terms, to give an expression for the electric field in terms of q and r and other variables like z, then my final answer now will be equal to It'll look like this. The Z component of the electric field is equal to Q, the total charge, times R, the radius of the ring, times Z, over 4 pi, because I now have in the denominator, I get a 4 pi and an R, right? So 2 times 2 pi R is 4 pi R. I can't forget the epsilon naught times R squared plus Z squared to the 3 halves. There's one last substitution I can make now. The R's cancel out, and I can finish this problem and say that the Z component of the electric field is just Q times Z times 4 pi epsilon naught times R squared plus Z squared to the 3 halves. And that is the electric field due to a ring of charge.